So here's our first question, and again, I'm just going to uncover the entire answer. Hopefully you've taken the time to do this on your own and not just looking at the answer and hoping to just glean something from it. But we have a right cylinder, and it doesn't have a top, and it gives me the surface area. And so again, that might be something I would have to look up the formula for. And this is the formula for surface area. Typically there's two of these because there's a top and a bottom, but because there's no top, there was no two. But here's what my picture looks like, and of course this is the formula for the volume because I'm trying to maximize the volume. So that's where those came from. Of course this guy I need to isolate so I can get one variable by itself. And I don't want to get r by itself because I don't want to square something that looks that ugly. So that's why I got h by itself. And then I plugged that back into my primary to find my reduced primary equation, my derivative, and therefore my critical values. I then found a feasible domain, which was 0 up to radical 3, based on the information given in the problem. And again, found increasing to decreasing, which means I had a maximum at 1. So the maximum is at 1, and I'm going to plug that back in to find that the maximum volume, or I'm sorry, the maximum radius then, the radius that I would use is 1, and the height that I would use is also 1. And that would give me the 3 pi feet squared. That would maximize the volume of the cylinder. Question 2. Again, I don't recommend going through these with me unless you've had a chance to do them yourself. But let's take a look. Here I've got a rectangle. They're telling me, hey, I cut out these guys in the corners. They don't exist anymore because I want to be able to fold the box straight up. Kind of a silly method for creating a box, but we get the idea. And I'm looking for the dimensions of the box with the largest volume. So that is what gives me my primary equation. I'm trying to maximize volume. And remember, volume is length times width times height. But I have to go with the length, width, and height according to my picture. So let's take a look at where these guys came from. I knew I was cutting a box into equally sized squares by taking equally sized squares from each corner. So I just called those X. It told me that the box was originally 3 feet by 4 feet. So this guy from here to here is 3, but I had to take away this X and this X to find this distance here in the middle, 3 minus 2x. I did the same thing here. This whole side was 4, and so I had to take away 1x and 2x to get 4 minus 2x for that side. So again, that's where my maximization question came from. Notice on this one, I didn't have to have a secondary equation because I used x for everything. So I simplified, then I found the derivative, and then I found the critical value. And I didn't show all of my work because this guy wouldn't factor, and so I used the quadratic formula. I just didn't do it here on this page. So I found two values, and again, I looked for what critical numbers I would use, or endpoints I would use. So I used 3 minus 2x equals 0. So x had to be 1.5, so I just looked at the smaller one of these. And then, of course, did my table just as I normally would. I found an increasing to decreasing, so this is a max, which helps me because I'm trying to find the largest volume. So this guy didn't even fit in, and 0.566, which of course was rounded to 3 places, would be where my max occurred. And again, I would plug it in to my original function then to find the volume, and the volume would be 2.868. So again, or sorry, not the volume, I apologize. The dimensions of the box, we didn't ask for the volume, so the dimensions of the box were x by 3 minus 2x by 4 minus 2x. So this was 4 minus 2x, and this was 3 minus 2x, and that's where I got my 3 values from. For practice 3, we're back to a cylinder. Again, that might require you to Google some formulas for surface area or volume of a cylinder. We are looking for the most economical can. So most economical means least cost. So here we're actually minimizing, which we haven't done yet, which means when I'm writing my function, it has to do with how much material that I'm using and how much it costs. So this is a picture of a cylinder, radius, height, etc. What am I trying to minimize? Well, I'm taking 2 pi r squared, so that's the top and the bottom, because there's 2 of them. I'm taking 2 of those times 10, because it says the material for the top and the bottom costs 10. The material for the side costs 8, so notice here I'm taking it times 8. So here's what I'm trying to maximize, but again I have R and I have H and I don't want them both. So I took the other formula, which gave me some information about the volume, and again I know it's volume because it's cubed, just like I knew that the other one was area because it was squared. So I took the volume of a cylinder and set it equal to 20 pi, isolated H so that I could then plug it back into my primary and simplify to have just one variable, and then find the derivative, and then find the critical values, which turns out to be just 2. Again, what are the endpoints? I didn't really bother trying to find an endpoint here. I just used infinity. I probably could have found something a little bit nicer, but you get the idea. Negative to positive makes me happy because that means it's a minimum, and that's what I'm trying to do, is minimize cost. So it happens when R is 2. So 2 is a minimum. I plugged in pi times, that should be 2 squared, not 22. Pi times 2 squared. H was 20 pi, so H was actually 5. The dimensions to maximize the cost of the cylinder are, minimize the cost of the cylinder are the radius of 2 and a height of 5 meters. Okay, let's face it, if you get this baby right, or any part right, you're doing a really good job. This is a tough question, mostly because it's really hard to visualize what's going on. So let's take a look at my cute picture. I'm standing at the edge. This is you, or me, I guess. Although I think that's a man, so we'll go with you. Which is 1 mile wide. So this distance from here to here. Whoa. Let me try that again. This distance from here to here is 1 mile. And I know that I can swim across the river. Look, I got a right triangle. That's exciting. I'm going to call this distance that I cover x, which means whatever distance is left over would be 1 minus x, because again it's 1 mile minus whatever part of a mile that I went through already. I can swim across the river at any point, walk the rest of the way. What route will take the least amount of time? So the minimize, maximize question has to do with time. So time has everything to do with each distance, right? I know in 1 hour I can go 2 miles if I'm doing this distance, which is swim. Notice Pythagorean theorem gave me that that distance is 1 plus x squared, square root. Pythagorean theorem. Then I looked at the fact that I'm walking 1 minus x, this distance, so I didn't ever go this distance. I went this distance, and this one is 1 hour for 3 miles. So now what? And again, you might be asking, hold on, usually we do 2 miles, 1 hour. Why did you do it backwards? Well, this represents miles, right? So if I take miles, let me do that up here. If I take miles times miles per hour, what is my final answer going to be? Miles squared per hour. That doesn't make any sense at all. That is why I had to flip this baby upside down and say, what if I took miles times hours per mile? Well, just like x's cancel or whatever, I end up with hours, which is what I want because it's time. So that's why I did it that way. From here, this is just simplification using algebra. Then, of course, the derivative And from here, I'm plugging in the 0 to find the critical values, and through much algebra, I find plus or minus 2 over radical 5. And again, I didn't bother trying to find an upper point, and that's okay. I don't really care too much about that part of it. So I found decreasing to increasing, which means that's a minimum, and that's what I want, is I want the least amount of time. So the least amount of time would be 2 divided by radical 5. And I could find that as a decimal as well. But 2 radical 5 is the minimum, and I'm going to swim to shore, and that's my x value, remember. So I'm going to swim to the opposite shore, going 1 minus 2 radical 5 miles from camp, and then I'm walking the remainder. Notice it didn't ask me for what distance did I swim. It just says what route is going to take the least amount of time. So I would have had to take this guy and plug it back in here if they said how long were you swimming. All I said in my conclusion is I'm going to keep swimming until I get 1 minus 2 radical 5 miles from camp, and then I'm going to walk the rest of that way.